So I'll present myself. I'm Maxime Dion. Everyone, welcome to this presentation on Introduction to Quantum Information. I'm working at Institut Quantique of Université de Sherbrooke in Sherbrooke City in Quebec. I think we have people all across Canada with us like today or tonight or wherever you are and whenever you are. And we have also Sean Wagner. I think he's a scientist, research scientist at IBM. He's going to do a presentation about career opportunity in quantum. So I guess you all can see my screen. Yes, all right. So the outline of tonight's activity or today's activity, I'm going to present a bit what is Institut Quantique at Sherbrooke. We're going to have some words from Sean on career opportunities. Then we'll have this first big block on introduction to quantum information. It should take us like around like mid part of this presentation. So maybe here we have like maybe 20 to 30 minutes of presentation, here another hour. And then we'll have this last part. So we're going to take a small break between activity 2 and 3. And then after the break, we can do an introduction to quantum programming, where we're going to use the quantum composer from the IBMQ website, so to build our first quantum circuit. So a few words. So oh, sorry, did I take the French version? No, okay, sorry. I just mixed up this first slide. So who we are. Myself, I'm part of a small team called the Espace IBMQ. So we are one of the, I think 15 or 16 IBMQ hubs right now around the world. So we're named Espace IBMQ, and we're part of a research institute called Institut Quantique, which is located in Université de Sherbrooke. So Espace IBMQ is now a small team of 5 persons. So there's Ghislain, who's a partnership developer. We have Jean-Frédéric, myself, and Marco. We are like the developer in quantum information. And then we have also Tom, who's at building the ecosystem and also social media and reach out for the community. So we're a small team, and so being IBMQ hub, we offer access to quantum computers from IBM to the people at the university, but also to other university and other members that might come along to team up with us along the way. So what is Espace IBMQ? So we're doing like mainly, we're acting mainly on 3 fronts. So on research, so we're helping the researchers at Université de Sherbrooke, and also we have one member right now called the CMAI Microsystem. You might know them. They have activities all across Canada. So we help our member to pursue their research. We're also building a community. We want to make people interested in quantum all around Quebec and Canada. So we're trying to build a community around academia, but also industry, bringing people together. And also the training part. So mostly what we're doing tonight is part of that. We're trying to build some material, bring people to learn more about quantum, being more familiar with these concepts, so that people can be efficient afterward in exploring the possibilities of quantum. So if you're interested in any of this, please reach out to us anytime. We'll be very happy to communicate with you. So what is Institut Quantique? Institut Quantique is a research institute that has been created, I think, around 5 years ago. It's based at Université de Sherbrooke, and right now we have more than 200 members. Most of them are students, and also we have like more than 30 faculty members a part of the institute. And what is very special about the Institut Quantique, and I've been a student there here before being working at Espace IBMQ. is that the student is very at the center of the research and all the activities around research. So, for example, each year there is the call for projects, and a student can apply for grants to build their own research project at Institut Quantique. And one of the result of that is that actually there is now a pretty nice culture of entrepreneurship. So here is 3 examples of startups coming out from research project developed by students at Institut Quantique and University of Sherbrooke. So we have SB Quantum, who's working on building magnetometer based on NV centers in diamonds. So this is like in the realm of quantum sensing. We have Cubic that is trying to develop a quantum radar. And also we have now Quantique, who's trying to build a new generation of superconducting quantum computers. So these 3 startups are based in Sherbrooke. Actually, I've studied with David, Jérôme, and Philippe, Julien, actually, around when I was around here in Sherbrooke. And also, if you're interested, we have several programs, both undergrad and graduate programs. So in physics, chemistry, engineering, computer science, and mathematics, and we try to put more and more quantum in most of these in these programs. So if you're interested, you can find information on the website of the university. And also maybe just to get you a bit more interested, we are right now, there's a new building that is being built. So the Institute was still out like an idea, but at the end of the summer, we'll have this new, very interesting building that is now taking shape. It's going to be the location for people to meet. Also, we'll have like 2 technological platforms. So one Quantum Fab Lab with a couple of dilution fridge, PPMS, and stuff like that. And also this quantum computing platform where like Espace IBMQ, for which I work, will be part of. So we'll have some computing capabilities to offer to our members and our collaborators. So on that, I think I can pass the mic to Sean. So I'm going to stop sharing my screen so you can share yours.
All right, just a mic check. You can hear me properly?
Yeah.
And you can see the screen?
Yeah, absolutely.
Okay, well, thank you very much, Maxime. So as Maxime had mentioned, my name is Sean Wagner. I'm a research scientist with IBM. I'm also a member of our IBM Quantum Ambassador team. So essentially what we do is we speak at events like this, and we're part of the advocacy program at IBM around quantum computing. So first of all, I'd like to say that IBM is very pleased to be partnered with the University of Sherbrooke on bringing the Espace IBMQ to the people of Quebec and beyond to help people learn about this very exciting technology and to put it into good use. So right now I'm going to talk about careers in quantum computing, which I think for the folks of you in the audience will be very interested. There's likely to be a tremendous amount of opportunity in the next little while, and so hopefully I can motivate you to consider a career in quantum computing. Okay, so what is the motivation for quantum computing from the start here? Well, these are some examples here that I'm showing of just industries that could benefit from just computing in general, right? So in fact, many of them have everything from agriculture to energy and chemical production to logistics, finance, and also in life sciences. And we built massive supercomputers that can say model a lot of the different processes and these things here, things like chemical processes or financial models for modeling investments and things like that. But there are limits as to what we can do with classical computers, right? So there are certain problems that we know that we can't tackle with any practically sized classical computer that's based on digital bits. And so we have to look towards other forms of computing, and quantum computing is one of those potential ways of doing things. Quantum computing, because we're harnessing some of the very basic principles of nature here, kind of frees us up to be able to explore an entirely new paradigm of computing that does things in a very different way, allowing us to explore many more possibilities for solving these types of problems. So as in the current day, what we see, where we see quantum computing really helping here are in these three areas, which I'm showing on the screen. So the first one is simulating quantum systems, artificial intelligence, and lastly, optimization problems. So in simulating quantum systems, this is things like simulating chemistry or simulating physics, right? And so we know that there are limitations as to what we can do with standard computers. In simulating these, we often have to make approximations to how nature actually behaves at that level. And so the reason for using quantum computers is to actually simulate these quantum systems using a quantum device that operates on the same principles. And so there's a tremendous amount of power in that. AI, of course, that's a very big and exploding area and just classical computing, but there are limits there too. We are approaching, models for artificial intelligence that are very large, right, and very unwieldy to compute. And we can never be sure that we actually got, the best and most accurate artificial intelligence model out of our classical computers. And so we're looking towards quantum computing to be able to refine those models, make them better through the training process, so we can get better pattern detection or fraud detection in financial use cases. And lastly, we have optimization problems. And optimization problems exist in just about every business, every field. AI, is basically an optimization problem in many respects. But we've seen optimization problems in key areas, mostly in finance, right? So think about, optimizing an investment portfolio, or, a bank trying to figure out, the optimal, say, interest rate to charge somebody on a loan. And so they have to look at also risk on, loaning people money. So these are all areas where we think, at least in the short term, the quantum computing is really going to make a big difference. So you have to ask, well, who's engaging with quantum computing right now? And so IBM has set up a system of engagement with us and our quantum team and researchers and resources, whereby we offer our access to our big systems, our big quantum systems, to solve these types of problems in real business cases, right? And so in many cases, we've established hubs like the SPS IBMQ at the University of Sherbrooke to help the community and region around there engage with quantum computing. But we've also engaged directly with certain industry partners. And so you can see on this list of partners that we've already engaged with, that we've made public here, they vary across very different industries here. So JP Morgan Chase, big bank in the United States, right? So they're interested in financial problems. ExxonMobil, big energy company. So they're interested in optimizing their energy production and chemistry processes, things like that. Daimler, they're a car company. And so they're looking at materials for their cars. They're looking at battery chemistry, all these sorts of things. And I'll get into some examples of what they're looking at presently with us. But there are many other industries here. And so it kind of cuts across a large swath of different things here. Not just also in the big partners that we have here, but also in the startups. So you see a very long list of startups here, and they're cut across many different things, including manufacturing optimization, drug development, financial modeling, all these sorts of things are in there. So there's ample opportunity in many domains where quantum computing can make a difference. So here's that example from Daimler. So they're trying to reinvent battery chemistry so they can make electric cars that go further or charge faster or last longer, just in general. And so that's a very tough problem. So they're examining a type of chemistry around lithium sulfur in order to be able to do this. And they're using quantum computing to model the chemical reactions that happen in the battery of these new types of chemistries that they're interested in. JP Morgan Chase, well, they're interested in their investments. How do they, simulate or make decisions about what investments to make? And so normally this is done using what we call Monte Carlo methods, right? Which are okay. They give a good estimate of what, say, the price of some kind of investment option or something out there, but there are limits. And so they're looking at quantum computers to be able to predict, say, the price of investment, in the future at a much more accurately than they could before. And then we have ExxonMobil here, and they're looking at ways of optimizing their chemical processes for producing fuels, for producing other chemicals, and also for producing just energy in general. So quantum computing can help optimize those processes. Okay, so then getting to careers, what's available, what is needed out there in the industry. So it crosses a wide swath of different things and different roles that need to be staffed, and a lot of these roles don't necessarily, exist or will exist very soon, right? Because as more and more partners, more and more companies are engaging with quantum computing. But we also need a workforce, right? People that are skilled, people that are trained to use quantum computers. And so, if we look at the top of this whole thing, we need people at the top, doing application development. So these are software engineers. These are also industry consultants that have domain knowledge about that specific area, whether it be like energy or agriculture or finance, right? So that these people understand the problems in that domain, but also understand how quantum computing can help solve those problems where classical computing can't. We need people in software R&D all across the whole software stack that you would get in, say, any other digital system there. So we need software architects to design, the whole flow of how data moves through the system. We need, people that are working on user experience and UI design, right? So that people can ultimately use the software which leverages quantum computing in the background without having to actually, work with the quantum computer itself at that low level. We need algorithms researchers, people who can actually develop, the types of computations that are happening on the quantum computer itself. And lastly, we need people who can do research in error correction. And I'll actually say that that's a very important area right now, because we want to be able to take the quantum computers we have right now, which are noisy, which are error prone, and turn them into machines that are fault tolerant, right? And so there's a lot of active research in that area right now. We also need people researching the hardware, creating better quantum bits, making better fabrication processes so we can make the quantum processors much more reliable or much larger or more robust. We need people that can work on the signaling. So a lot of the signaling is done with microwaves right now. So we need engineers experienced in that area. And we also need people that are experienced in cryogenics. So these quantum processors need to be chilled down to nearly absolute zero in order to operate properly. So we need people designing these dilution refrigerators that are able to do that. And lastly, we need people in ecosystem development, people who can go out into the community and spread the word about quantum computing, who can engage with clients and students and researchers, provide them with the tools and understand how the tools work and how they can be leveraged by those various people. So in order to get into one of these roles, what skills do you need? Okay, so there was actually an article that was written by a colleague of mine named Aggie Branchik, and she's actually based here in Ontario. And she wrote this article here, what skills do I need to work at a quantum tech startup? I think it's a little bit beyond, you can go beyond just startups, right? You can actually go just across any industry player out there, any company that will need these types of skills. And so what she found is that a lot of the startups that she interviewed were saying that they want domain experience. And I mentioned that before. We need chemists, we need physicists, we need healthcare professionals and people who are working on drug discovery and medicine. We need people working in operations research and business process optimization. We need people in finance, people who understand the problems that exist in each one of these industries and know how to apply computing to it. Programming, again, you're going to need some basic skills in programming in order to engage with quantum computers. So learn Python. A lot of the frameworks for programming quantum computers are done in Python, so it's a valuable skill to have. C and C++, of course, that's a very standard programming language to know. Lastly, on this note, learn some quantum algorithms. And there's lots of resources that are available online. I'll show you some in a minute here. But leverage the resources, courses, textbooks, online blogs, about algorithms, and learn a little bit more about them, how you can use them. When it comes to mathematics, it's all based on linear algebra. So if you have a good solid foundation in linear algebra, to work with matrices and vectors, which kind of the content in a second year math course in university, that's probably sufficient for being able to do the work in quantum computing here. If you're going to get into the hardware, know your electromagnetics and microwaves. Optics is also going to be an important component of quantum processors in the future, we think. And also know your quantum mechanics, right? Because we are talking about operating devices that exploit these properties of quantum mechanics. Lots of resources out there in order to get you skilled up on being able to work with quantum computers. And the good news is a lot of it's free. And IBM has actually made a lot of this content available for free. So for instance, we have an online textbook called the Qiskit textbook, open source. Anybody can read it. It's got lots of programming examples as part of the overall flow of the textbook. It's well worth going through. Again, there are blogs on our Medium page. We have video series on YouTube. We have tutorials. We organize camps and a summer school. So there's actually a summer school coming up in July. So if you just search Qiskit Summer School, you'll be able to find some more information about that. There's lots of community engagement there. So we have a Slack channel that you can subscribe to there at qiskit.slack.com. I suggest you also subscribe to some of the social media channels on Twitter and LinkedIn there for up-to-date news on what's happening in quantum computing. There's some projects out there that you might want to engage with, including the Quantum Open Source Foundation, which is trying to make a lot of the software around the quantum ecosystem open source. And of course, there are courses online that you can take from various online course websites out there. So that's what I have to say to you here. So I hope that this has been helpful. I hope that you'll be inspired to go out there and think about a career in quantum computing. And if you are, being in this workshop today is a good start. Thank you very much.
All right. Thank you, Sean. So yeah, I think that here it's like being here is a good place to start. I've been working in that field for only the last year, actually. I would say that you need to start somewhere. I think this workshop is going to be very introductory, but if you want to tackle a very large problem and very important problem, you need to start somewhere. And we have a really broad audience also today, folks. So maybe keep that in mind. So we're going to cover the very basics today about the quantum information theory and quantum programming. It's going to be very, very basic, but it's going to make afterward whatever level you're going to work with. Are you going to work directly with the quantum computer, or you're going to use a quantum computer in your career? Being able to understand these concepts is going to make you quantum aware. So I think, as Sean is saying, it's a very good start. So I'm going to share back my screen. And I think we can get going. So if during the presentation you have any questions, I encourage you to put them into the chat. If it's related directly to the presentation we're seeing right now, I'll be happy to answer these questions. I think it would be nice if we have a bit of interaction. If you have questions on quantum computer and quantum computing in general, I think we can maybe keep these questions for the end of our presentation, and we can have maybe a discussion. So yeah, so we have like a question that maybe is a bit broad in the chat. Maybe if Sean wants to answer that in the chat, I think it would be nice. But right now, I'm just going to concentrate on the presentation we have at hand. So we're going to start with what's a quantum computer, okay? So this is a quantum computer. This is a beautiful image provided by IBM. This is, roughly speaking, this is a large chandelier that goes into a very cold environment. So the idea here is that the quantum computing, actually, the quantum computer is probably just a little chip around here. And all around what this is wires that are connected to this chip that makes it possible to interact with the chip. And all the layers that are there to make sure that this chip is in a very isolated environment. So very low temperature, as Sean was saying, very low noise, and you are interacting with it only when you need to. So this is the idea this is a picture of a quantum computer, and so the idea of a quantum computer. So why do we where the idea is coming from? So the thing that we know is that nature is quantum, like matter is quantum by nature, or quantum nature of matter. Okay, so the matter around us behave into a quantum manner when we look at it like very closely on a very small scale. So this is a given. Then from that we can infer some quantum logic, and by that what I mean is that there's three phenomena that are very important in quantum mechanics and quantum physics. They are superposition, entanglement, and interference. So especially superposition, entanglement, there is no common phenomenon in the classical world that relates to that. So the idea of this is, can we use this phenomenon to build a quantum logic that will help us to do computation in a different way? So this is something that is outside of what we are used to think in our classical world. So the idea here is that can we use this quantum logic to tackle difficult problems using a quantum computer? So by difficult problems, what I mean some difficult problems that we know in certain area, like molecular simulation to design like new drugs, artificial intelligence related to machine learning or stuff like that, optimization, environment. So any kind of optimization can be applied to maybe design new solar panel that are going to be more efficient, or we can maybe use more effectively the resources that we're already using. And also maybe in finance, there's an optimization problem there that can be solved. And also in cybersecurity, there are some difficult problems that the quantum computer could help also. So by difficult problems, what I mean usually is that these are problems that cannot be solved on a classical computer, even a super classical computer, in a given time that is reasonable. So if it takes 10,000 years to the best classical computer on Earth, then this is a difficult problem. And the promise of the quantum computer is to be able maybe to tackle this problem at some point. So before we go into the quantum information, I just want to make sure that we're all covering the same ground and we have the same fundamentals, and we're going to talk a bit about classical computing. So how does classical computing is done? So there is the most fundamental unit of information that we call a bit, and a bit, is either 0 and 1. So it can be only one of two things. We label them 0 and 1, but actually it could be anything, but we label them 0 and 1. And then with a bunch of zeros and 1, you can encode many, many things. For example, with 5 bits, I can encode the number from 0 to 31. I can encode 32 different objects. Here the number 0 from 31. I can also encode the alphabet, for example, with the first 27 to 26 combination, and then I have some space for other character I could use, like maybe a dot or an exclamation point and stuff like that. So using 5 bits, I can create 32 different combinations, and then I can encode some information in there. So that's nice. I can encode information, but if I want to do calculation, I need to be able to transform these bits. So for example, if I want to add two numbers, I know how to add like 6 and 12. It gives me 18. I have this table of addition here that I know because I went to the kindergarten. But how does a classical computer does it? So for 6, the classical computer has a binary representation of it. I can go into the table and I see that 6 is 0, 0, 1, 1, 0. And I know that 12 actually in the table is this bit string. And then I can add them. And the table for adding these numbers is very simple. So if either 0 gives me 0, if one of those is 1, it gives me 1. But if both are 1, then I had to add another one on the next bit. So if I do this addition here, it's pretty simple. 0, 0 gives me 0, 0 and 1 gives me 1, 1 and 1 gives me 0, but I push another one here on that side, and then I have 1 plus 1 gives me again 0, but I need to push the 1 here. So I have this overflow. So this is how like addition in the classical computer works. So that's that. So if I want to do calculation, I want to do something interesting, I need to transform this information. So that is in the realm of the ideas. This is very abstract, but actually when I was saying that the bits can be either two things, we labeled them 0 and 1, but actually they need to be supported by a physical system. And actually, like for example, if I have a bunch of switch like that, if I say that when it's off is 0 and when it's on is 1, then I could build a computer with a lot of these switches. If I had like 100 of these switches, I could build a very simple computer, and not very powerful, but I could do it. And I just need to label these two different states by 0 and 1. There's another way, another physical system that we use to encode information. It's with micromagnets, with magnetism, like in the hard drive, depending on in which direction the magnet was pointing, we can say that it's either 0 and 1. So this is what we call like the physical support for the information. And then we can kind of build kind of a hierarchy of ideas and abstraction. So we start with this physical system, and then we build like abstract information out of it, saying that these are 0 and 1. And then we can transform them either by building more abstract information, building numbers and letters, and then building words with these bits. And then we can transform that with the logical gates. So this is like with maybe assembly programmation. And then at some point we go up at a more abstract level, where now we're using maybe Python or C, C++ to interact with these bits, but at a very much higher level. And then at some point we finish and we have some applications, some apps that we can use and perform certain tasks with these. So this would be maybe a very crude overview what like classical computing would go from like the very basic to the very top. So this was just a brief summary of what classical computing is. And before we go into quantum computing, I just want to make some experiment. So we're going to introduce quantum as most natural way, I think. So we're going to look at what the light spectrum of atoms. So the experiment we're going to do is going to take this bulb and we're going to put some gas in it, like for example, hydrogen. And then what we're going to do is going to apply a voltage on these electrodes, and there is an electrical current is going to flow through the gas. And this electric current is going to excite the atoms. The atoms are going to emit light, and we're going to have something that looks like that. So so this is a hydrogen lamp, and why does hydrogen gives you like this kind of pink or purple color? So we're going to try to understand that. So to do that, we're going to use this Pink Floyd image. Actually, we're going to use this prism to like disperse the light. So we're going to divide the light using the dispersion into a prism. So you know that white light actually is composed of all the visible light, all the different colors. But if you take the light emitted by a hydrogen lamp, what you're going to see is a spectrum where you're going to have some discrete colors in there. So you have a background of color that is just there to show you like all the colors of the rainbow. But actually, if you use an hydrogen lamp and make it pass it through a prism, you're going to see only this red color, this light blue color, this purple one, and there are even like darker ones, but mostly you're going to see just specific colors. And so that's interesting. And if you change the gas inside the bulb, like if you put helium, you're going to still see some discrete colors, but they're going to be at different places, different colors and different wavelength. So the color actually of light is related directly to the wavelength of that light. And then you go and for like heavier atoms and you see it's still discrete, but you have more and more rays in the spectrum. So what does it do that? And the answer actually is, maybe it's the easy answer, but it's quantum mechanics. And we're going to try to understand this. So what does happen when we're exciting, what does it mean to excite an atom? And actually what we mean here, so this is like a very crude and like outdated representation of an hydrogen atom. So we have this nucleus that is only one proton, and we have one electron that is rotating around, okay? So when we excite an atom like that, what we actually mean is that the electron is going to gain energy and is going to go on a higher level of energy, okay? And these orbitals around are actually energy levels. And as you go away from the nucleus, you gain energy. So the nucleus is positive, the electron is negative. They want to attract, they want to be together. If you pull them apart, it costs you energy. And these levels actually are discrete. So they are on a ladder like that. They are not evenly spaced, but they are discrete. They're quantized, and therefore, we're going to see some quantum mechanics phenomena. So as I was saying, this electron, when it's excited, it goes into a higher energy level. So what's happening on the energy scale? We might say, oh, the electron is going up and is going to go on the higher energy level, but this is not the right picture. So actually, the electron can only occupy either this level, or any of these levels. Cannot be in between. Needs to be one of these specific energy level. So the picture of taking it and going up like that is not quite right. What we should like draw is that the electron is slowly disappearing from one of the level and is slowly appearing on the other one. So this is mostly, like maybe it's just a better representation of what's happening. The electron cannot be in between. It needs to be on either one or the other, but it can slowly disappear from one and appearing on the other level. And then at some point, the electron is going to relax, it's going to go down back on the lowest energy level. It's going to, and by doing that, needs to release some energy. It's going to release the energy in the form of a photon, and this photon has a specific energy, as this energy, like the difference between these two levels, is going to emit a photon of exactly, yeah, all right, Sean, that's all right, yeah. So thank you. Oh yeah, so the electron, when it loses its energy, is going to emit a photon that has exactly the energy that is between these two levels, and to this energy corresponds a specific color, a specific wavelength, and a specific color. If the electron was excited in the higher level, the light that is emitted is of higher energy, and it goes towards the blue colors. So here I represent this as a green photon, and here is a blue photon. To be exactly, to be a bit more exact, actually, this one is not the lowest energy level in the hydrogen atom for this specific spectrum. There's another level that is a bit lower, but the transition from these level to this lower level actually are into the ultraviolet range of the spectrum, so we don't really see it. But the basic idea is still there. So because we have discrete energy levels, the light that we're seeing is discrete, and it corresponds to the difference between these levels. So this is like quantum mechanics introduction as simple as possible. Then, so this is all right, but can we build a bit out of this? Can we say I want to encode information in the energy level of an hydrogen atom? So the idea here is this. So if I want to do this, I could use the two first energy level of an hydrogen atom. I can label them 0 and 1. And these label here with like a stick on the side and an angle on the other one, this is very, like, it's called what we call the Dirac notation. It's when you see something like that, you know that it's something quantum is happening. Okay, this is really a quantum notation, but just see this as labels. It's labeling, I'm labeling this as the state 0, and I'm labeling this state as state 1. And because we're using this Dirac notation, we're going to do quantum with this at some point. But for now, maybe you just see this as 0 and 1. So if I say that when my electron is on the lower level, I'm in the 0 state, and when I'm on the first excited level, I'm in the 1 state, I could take like a hydrogen atom and build a qubit out of this. I build a bit first. And then all the other levels that are higher, I just forget about those. So this would be maybe a possibility to build a classical bit. But what I need to do also, if I want to do calculation and I want to do computation, I need to be able to control the state of this qubit. So how do you control the energy level, the energy position of an electron in an atom? What you can do is actually you can shine light on it. So if you shine light exactly with the energy that is between these two energy levels, you will see something where the electron is going to slowly disappear from the lower level and it's going to slowly appear in the first excited level. So like if I plot in function of time where the electron is, what you're going to see is going to slowly disappear from the lower level and slowly appear on the top one. What is more interesting, even after that, is that if you continue to shine light on this system, the electron is going to slowly go down in the lower state. And if you continue like that, you're going to see an oscillation, actually. You're going to see the electron going from the lower to the first excited level and oscillate between the two. But what is most interesting here and what makes this different from the classical bit and why we can do a qubit out of this is that if you look here at some point like here, so for example, you shine light for a certain period of time, but you stop at that point. So if you stop there, what you see is that your electron is at both in the 0 and the 1 level. It's there on both at the same time. So we can represent this a bit like this with just like a bit of fadey red dots. And this is what we call quantum superposition. So this is a superposition of state. The electron is into a different energy level at the same time. So what does it mean? What happens if, for example, I have this kind of qubits and I try to observe it? Okay. So for example, I have this qubit here. Now this is a qubit. I've prepared a superposition of 0 and 1. I would say like an equal superposition. And then I measure it. I take a look at it. I try to see, is the electron in the state 0 or is it in the state 1? And when I do that, actually, I'm going to find either one answer or the other. I'm going to find it maybe in the state 0 or maybe in the state 1. And I should have like 50% to find it in one state or the other. And then if I remeasure and I do another measurement, I look at it again, then there's nothing that is going to change. If it's in state 0, it's going to stay in state 0. And if it's in state 1, it's going to stay in state 1, unless I make other manipulation of my qubit. So another way to say that is that if I prepare like identical, like maybe 100 qubits like that, with identical preparation, an identical experiment, and I do the same measurement on the 100 of those, I'm going to measure around 50 of those in the state 0 and 50 of those in the state 1. There's some uncertainty to that. So I might have like 48 and 52, for example, but this is like purely random, and we cannot like predict this. But there's not only like equal superposition that I can prepare. Actually, if you look at this at this time here, you can see that you can have superposition that are not 50-50. For example, here at the beginning, I was 100% in the state 0. But at some point here, I get 50-50, but I could be like 3/4 in one state and 1/4 in the other state. So superposition actually is a continuum. I can be completely on one side, completely on the other side, but I can be any way in between. So this is what we call quantum superposition. So if I try to make a bit of a summary of that, so these are the main points of a quantum superposition. Quantum object can be in many different states at the same time. So this is something that doesn't occur in the classical world. The superposition of state can be in a continuum of different proportion. And when I measure a qubit, I'm going to measure it either in 0 or 1, and it's going to be completely a random process if the state was in the superposition. And the probability of getting these two results only depends on the state of the qubit before the measurement. And once I've measured a qubit, the state is defined. It's going to stay in there unless I do other manipulation on it to re-prepare another superposition. So maybe I can just take like 30 seconds just to see if there are some question in the audience. Like right now, I can maybe just to see if there are some questions. So there is a question in the chat asking, is the 0 and 1 the spin of the atom? Actually, in this example, no. So the 0 and 1 are the energy levels. So for example, for a nitrogen atom, you have like this 1s orbital, 2s orbital, 2p, for example. These here in this example would be this. That being said, there are some quantum computer architecture that are using the spin of an electron to encode the information. So for example, spin up would be 0 and spin down would be 1. If you can prepare superposition of these states, if you can control them, then you could build a quantum computer out of the spin of the electron. So that's a nice question. Okay, so we have many questions. So okay, what is exactly the measurement? I'm a bit confused how it can be either 1 or 0 when we measure if it's superimposed in both places at the same time. So this is a very tricky question. So the measurement actually is something that is very much complex, but maybe I can tell you kind of an analogy. Yeah, maybe the analogy is not that great, but maybe you have already heard of the Schrodinger's cat. So the Schrodinger's cat, the experiment proposed by Schrodinger to say that quantum mechanics is a bit foolish, but actually he was wrong. But the idea here is that you place a cat in a box with an atom that can be that is radioactive, and it's going to decompose at some point, but you don't know when, but you know it's going to do it. And then related to that radioactive atom, you put poison, like a bottle of poison, that when the atom is going to disintegrate, it's going to release the poison in the box and it's going to kill the cat. I'm sorry, it's a very morbid analogy, but that's what it is. So the idea of the thought experiment is that the state of the atom might be in a superposition at some point. You don't know if it's disintegrated or not. And as long as you don't open the box, maybe the disintegration had occurred or maybe not, but as long as you don't open the box, you don't know it. So you cannot see if the cat is dead or alive. This is just a thought experiment. It's not very a very nice explanation to see what the measurement is, but it's kind of something like that. Another way to put it would be to say that actually to measure something in the quantum world, you need to be in interaction with it. You need to connect with it. But you need to interact with it. So you need to touch it actually. So in some way is that when you are in a superposition of state, you are in a very like delicate equilibrium. But when you're going to observe it, you're going to perturb this, and you need to choose 1 or 0 or 1. There are some experiments that you can do, like for example, with polarizer and polarized light, that can be a bit more insightful. But I don't want to go in the direction right now. So there's a question by Thomas. So when you observe it, it will appear to be in both positions at once. Actually, no. When it's in the superposition, is because you're not interacting with it. You're not looking at it. You cannot interfere with this superposition of state. It's really when you're going to interact with it that it needs to choose one of both possible results. So just to make sure I understand, the measure value of the qubit will be dependent on time. So if I come back to this slide, so maybe this one here. So if I shine light continuously, the state of the qubit is going to oscillate between the state 0 and then state 1. It's going to oscillate between these two. But at some point, if I stop shining the light, it's going to stay in the state where it is at that time. For example, if I stop at that time and then here I stop shining light on it, then it's going to stay completely in the state 1, and it's going to stay there as long as I don't interfere with it. On the other hand, if I shine light up to that point and then I stop the shining light, it's going to stay in the superposition. There are other phenomena that's going to perturb that, that makes that the quantum information is very fragile. There is something in the environment that wants to interact with this. There's many atoms around, stuff like that. So it can, like what we call it, it's going to decohere, and we're going to lose the quantum coherence. But like in a completely thought experiment to look at this, yeah, it should stay completely in the superposition as long as you don't interact with it. I hope I'm not missing too much question, but are there any theory as to where the electron goes or where it travels between the two positions? So, so here what I'm asking you to do actually is to forget about what you're accustomed to, like where should be the electron. Actually, this theory is very, very valid. It's verified in labs like every day. You need to deconstruct what you think you know about the world, because you've only interacted with the classical world up to today. But when people like physicists are doing experiments in the labs, like the phenomenon they're looking at can only be explained when you need to change this paradigm that you have. So if quantum mechanics is saying that an electron is in two different energy levels at the same time, that's really what's the best representation of reality that we have, even if it doesn't make sense at our scale. So what does interacting with it in this context mean? So yeah, so I'll have to continue on the presentation, but I find your question all very, very interesting. So maybe I can insert this last one, and maybe we can keep a couple of these one for maybe later on. So what does interacting with it in this context? So interacting with for example, in the context of an hydrogen atom, we know that we can control the state of the electron by shining light on the atom. If we shine light on it, it's going to oscillate between the two energy levels. How could we measure in which energy level it is? So like on top of my head, I don't know, I didn't do these experiments, but for example, if these two energy levels are like 1s and 2s, so like the shape of the electron is going to be much smaller for the 2s than for the 1s, the opposite, sorry. So that the shape of the position of the electron, like the mean position, the average position, the average distance between the nucleus and the electron is going to be different. So if I have some means of measuring that, then even if I prepare my electron into a superposition of these two energy level, at some point, if I'm trying to see in which of these two energy level it is by measuring what is the average mean between the nucleus and the electron, it could be a way to force the electron to decide in which of these two energy level it is. So so thank you for your question. I'll need to just keep continue a bit, but if you don't mind, maybe completely at the end of the presentation, we can come back to this question. I really like the fact that you're very eager to learn new stuff. All right. So at that point, what I want to do is to introduce you to what we call quantum parallelism. So quantum parallelism is a way to exploit superposition to make computation in parallel. So the idea is this. Imagine that this is a classical bit. Okay, I have like this outdated green color to make it appear classical. And I have this question. I have a function here that is going to take as an input one bit, either 0 or 1, and it's going to compute a value out of this. And I don't know what this function is. I can call it, but I don't know what it is. So when I call it, it's going to, I can call it like this, asking what's the function where the bit is 0. And this is going to give me some value. And I can call it with the bit 1, it's going to give you another value. And my goal is to find in which position this function is minimum. So here to identify where the minimum is, I need to evaluate the function twice. I need to evaluate for 0 and I need to evaluate for 1. But can I do something different with a quantum bit? So here the idea, and this is a bit more abstract, is I'm going to call this function on the superposition of two states. Okay. So by doing this, what I'm actually doing is I'm computing at the same time the two different possibilities. I'm computing them at the same time, but the result that I'm getting by evaluating the function of superposition of these two possibilities is I'm going to get a superposition of the two answers. Okay, so that's why here I made them a bit shady, is that applying this function on with an input, actually giving an input that is a superposition, is going to produce a superposition of the result. And then I can measure the result. And when I do that, I'm going to get one of these two results. But I don't know what is the input. So I don't gain much here. So maybe I'm not just like a very good seller, what I'm trying to convince you that is like marvelous and super interesting. But like here, the idea, the idea is not complete, but the idea first is that I can evaluate function using a superposition of input. And by doing that, actually, I'm evaluating both results at the same time, but I need something more to make something interesting. But like keep with me, and I'll try to convince you that it's kind of interesting. So what happens if I have 3 bits? So if I have 3 bits, there's 8 different possibilities of inputs. And then I have 8 different possibilities of outputs. So if I want to find the minimum, the classical way usually to find a minimum usually is we need to evaluate a linear, something that's going to scale like linearly with the number of input that I can give. It depends on what is the kind of optimization that we need to do. But here, for example, if I have no idea what this function is, I need to evaluate the function 8 times to be able to evaluate where the minimum of the function is. On the other side here, if I have like 3 qubits and I prepare the superposition of these 3 qubits, I can evaluate all the 8 possibilities, the 8 different outputs all at the same time. But here again, if I take this output and I'm taking a look at it and I measure it, I'm going to select one of these 8, and I will not know from which input it's coming from. So, but the idea here, and this is something that is a bit out of the scope of the presentation, is to use something called quantum interference to make some of these possibilities more probable to be measured than others. So you remember that the superposition we were saying, I was talking to you about before, can have different proportion. So there are some tricks to make sure that actually that the result that we want to measure are going to be more probable. For example, here, I could apply an interference pattern that would make this result be more probable to be measured than the other ones. So like, to represent this like graphically would be doing something like this, okay? By making some possibility more probable to be measured, I'm going to have a better probability to find this value. So for example, here, maybe I could evaluate my function 2 or 3 times. And if I always find the same one, it means that it's probably the result that I'm looking for. So here I would pass from having to evaluate a function maybe 8 times to 3 times. This is not a huge gain. But now we need to go a bit further. 300 bits. So 300 bits in your computer, it's nothing. Okay, yeah, you have you have billions and billions of bits in your computer. But how many? If I want to find a minimum of a function that takes 300 bits as an input, there's 2 to the power 300 different possibilities of inputs. So I would need to evaluate the function this number of times. And just to give you an order of magnitude of what this number is, this is the number. And this is roughly the number of atoms that there are in the universe. So if I had to evaluate the function for each atom that there are in the universe, I would be, maybe I would be missing some atoms to finish my calculation. So 300 is not that much. So like quantum computers with 300 qubits, we're not there yet. Like at IBM, the largest quantum computer is at 65 qubits. But 300 qubits is not science fiction. You know, it's going to be there maybe in 1 year or 2, okay? So this is not completely foolish. And we could apply this kind of scheme of what we call quantum parallelism to evaluate this kind of function, apply some quantum interference to that to make sure that we're trying to optimize some function. So the idea here is that we're exploring like a space of possibilities that is not even like possible to explore with a classical computer. We're exploring a lot of different possibilities with a quantum computer, like a space that is so large that it cannot be stored into any classical computer. So with that, I hope I've blown your mind, okay? So this is quantum parallelism. So quantum parallelism is it exploits superposition to explore many different possibilities. So 2 to the power n all at once. Okay. So 2 to the power n, you just can compute it on your like your calculator or on your computer, and you're going to see that like 2 to the power 60. I think you can even like generate that number on your computer. Then you can produce a superposition of all the possible different results of this function. And then after that, you need to apply clever tricks using quantum interference, try to make some of these different possibilities more probable, dependent of like maybe the value that they're going to give you are going to be smaller. And you try to boost the probability to measure these specific possibilities. And then it's going to be easier to find, for example, the minimum of a function. So that was quantum parallelism, okay? Now, what I want to talk to you is entanglement. So if superposition is weird, entanglement is weirder, okay? but I'll try to make it as clear as possible. So quantum entanglement, or you can maybe like intrication also is a term that is sometimes used, is the property of a quantum system to be in a superposition, but as a system. So what I mean by that is this. So take, for example, these 2 qubits. These 2 qubits here, I could place them into a superposition, both independently. They are in the superposition of 0 and 1. And if I measure both of these qubits, I will find either either one we're going to be in either 0 or 1. Okay, so there's 4 possibility of measurements. Okay, yeah. So if I measure these qubits, these are the 4 different possibilities. Either I find both in 0, either I find one in 1, the other one in 1 and in 0, the opposite, or I find both in the 1 state. So these are the 4 different possibilities. If I have an entangled system, the entangled system is the property actually that the state of the 2 qubits are correlated. They're not independent. Okay, and if I have something like that, so this is the way I'm trying to draw this, try to represent this graphically, and then I measure these qubits, I'm going to find either both of them are going to be in the 0 state or both are going to be in the 1 state. But the cross possibilities, 0 and 1, 1, 0, are not possible. Okay, I can only find these 2 different possibilities. So what I was saying a bit earlier, this is the property of a system to be in a superposition of state. So it's the whole system. It's either both 0 or both 1. It's in superposition of these 2 possibilities, but the other one are not possible. So this is entanglement. And what's very weird with that is that imagine that I have these 2 qubits and I've prepared them in a quantum superposition, in quantum entangled state. And then I can go away with one of the qubits. For example, I push these 2 qubits to both corners of the universe, okay? And then I measure one of the qubits. I measure the qubit on the left, for example. And I measure it, I find it in state 0. This means that the other qubit is now in the state 0. Even if nobody measured it, if nobody has done anything with it, I know that it's in the state 0. And if I measure my qubit on the state 1, I know that the other one that is at the other side of the universe is going to be in the state 1. And if somebody at the other end of the universe measure the qubit after I've measured them on my side, you're going to find these same results. So this is not science fiction either. This is kind of experiments that are done in labs now frequently. This is something that has been done between Earth and a satellite in space, stuff like that. So this is something that is very real, and it's a real quantum phenomenon. Okay. So we've seen, yeah. So I have in the chat the spooky action at a distance. This is the name that Einstein didn't like entanglement. It was defying his beliefs. So yeah, he called that spooky action at a distance. I don't know how to say that in German. I'm sorry. I should learn it. So we've seen quantum superposition. That is very nice to do quantum parallelism. We've seen entanglement. That's going to be very useful to do quantum computation. So we've covered these 2 topics. Would be nice to cover also interference, but given the time that we have, this is the 2 main topics that we find interesting to cover. So we've seen, I've shown you this picture at the beginning. We've seen superposition, entanglement. Interference would be also nice to cover, but basically the idea after in the second part of this workshop is going to be using superposition entanglement to do something that is maybe not it is not very common and not very familiar. We're going to study the teleportation algorithm. So how can you teleport information using superposition and entanglement? So just before we take the break, there's just a couple of information that I want to share with you. So at the beginning, you remember that I was saying that the classical bits need a physical system to be embedded in, and we need to have something to encode this. And actually, there are a couple of architecture that are a subject of research right now. So the idea of using hydrogen atom to do qubits, hydrogen atom is probably very not suitable for that, but using atoms as support to encode quantum information, this is not a silly idea. And some people are using trapped ions. So they're trying to make some atom float on the top of a circuit. and then they address these atoms using laser, and they use the state of the electrons in these atoms to encode some information. So this is something that this is an active research subject right now. There are the superconducting qubits, so also called artificial atoms. So the idea here is to use superconductivity and also a specific component based on superconductivity called the Josephson junction. And actually what you're creating with this is, if you've done a bit of electrodynamics, you're doing an LC circuit, but the LC circuit, when you go at the quantum level, it's discrete in energy level. But using the Josephson junction into the area, there's some anamorphicity that is there. So making that these energy level are not harmonic, they're a bit different. So they look like a bit the energy level in an atom. And actually, this is the technology that Google and IBM are using in their quantum computer. So this one is very promising, is very advanced technology. So there are other architecture also, the spin qubits. We mentioned it a bit earlier. Spin qubit is something that is studied here in Sherbrooke in some of our labs. So using the spin of the electron to encode the information of a qubit. And also you can use photons. So light, photon are quantum in nature also. I'm not as much familiar with this kind of architecture, but there are some very nice startups even here in Canada. So Xanadu is doing this kind of a quantum computer. So the interface between a classical and the quantum computer, you're going to see it's still like we're not going to replace our classical computers with quantum computer in the near future. Like the quantum computer is a very specific and specialized tool. But to control it, we need a bunch of stuff around it, and we probably also always need a classical computer. So, but here I'm just trying to make like the parallel between the two. This is the physics support of the information. Here on the classical part, we have 0 or 1, but on the quantum part, we can have 0 and 1 at the same time. This is a notation that we're going to see in the second part. This is the direct notation. But the idea is that we can, here on that side, we can prepare some numbers, but on the other side, we can prepare superposition of numbers. And here we're coding with using maybe Python or C++, but actually here the language of the code they're going to use are quantum circuits. So the quantum circuits are like the basic elements of what we're going to implement to make some calculation. This is a bit like assembly programmation if you're familiar with this. So this would conclude the first part of the talk. I think we can take maybe a 5-minute break. Actually, before we take the break, maybe I can just take a look at a bit of the question that we have in the chat. I think I've left some back there. How does the principle of superposition apply to the real world? Or how does it help? So, so the principle of superposition at our level, it doesn't exist. Something that you can see, as I was saying with light, if you play with the polarizer and polarized light, actually you can see that, for example, if you're familiar with this, if you prepare polarized light, like maybe at a 45-degree angle, and then you use a polarizer, either to try to make it vertical or horizontal, you can see actually light, the photons, to be in a superposition of these two. And you shine light that is polarized this way and make it passing through a polarizer that is like that. It's trying to measure it like this, or you're trying to measure it like that. But actually you can get both results. So I don't know if there is in the real world, what are the superposition. I'm not sure I can really answer this question. We have also the measurement can only be done in the vacuum to avoid unintended interaction. So yeah, so if you really want to do a measurement on a quantum system, and then you're going to see like quantum phenomenon, you need to have like the most like basic interaction with it. You need to have no noise at all around. You need to have, like, the environment should not be able to interact with your system if you want to be able to measure it and see some quantum effects. So yeah, so I like the comment that quantum mechanic, it's applied to the macro world. It's not our common sense. We have a question by Pierre-Luc asking, how do you entangle two electrons? Okay, maybe two electrons is a bit difficult, but there are what we're going to see in the second part, actually, we're not going to entangle electrons, we're going to entangle qubits. So we can see in qubits in the more abstract way. And the second part, we're going to entangle qubits. And to do that, actually, what we're going to do, we're going to apply what we call 2 qubit gates. So yeah, maybe stay tuned for the second part. Abra Hussein asking, does qubit have any relation with nonlinear optics? Actually, I'm not a specialist of like optical quantum computer like Danet Zena do, but I know that nonlinear optics is very important for that. So if you want to look it up, I think you're going to find like some relation. Earlier, when we talked about superposition, why are we measuring specifically the minimum of the suppose function rather than any other value? So this is just an example of a problem of optimization. You could try to find where is the minimum, or you can find where is the maximum, or you could try to find where my function is closer to a certain specific value. So this is just how you define your optimization problem. You can always make this kind of problem being a kind of minimization. You can always try to find, for example, if you're looking for a specific value, you could look, well, where is the minimum between my function and this specific value? How I make the subtraction between the two, and I'm trying to find where it's the minimum. So in photography, we use polarized filter to be able to take darker picture in light of day, and polarization is part of the quantum world. Yeah, so actually, when you're using polarized filter for photography, I do a bit of photography myself. Actually, it's because the light coming from the sky is very much polarized. So it's polarized. So when you have the sun like that, it makes a plane with the horizon. And actually, the light is polarized perpendicular to that. So if you have some paralyzer and you look at the sky, but at 40, so the sun is here, look in that direction, and you turn your polarizer like that, you're going to see the sky that's going to get darker and lighter. So you have a question: is the summer school, the Cascade Summer School, particularly expensive? Actually, I think it's free. So Sean didn't say it, but if you want to subscribe, I think the date, the opening is the 26th of May. So yeah, but I think it's free, but I think the places are limited. So you need to be as fast as possible to subscribe to it. Is quantum tunneling something that affects quantum computing? So this is a nice question. So for example, when I was talking to you about the superconducting qubits, I mentioned something, the Josephson junction. So the Josephson junction actually is a result of quantum tunneling between two superconductors through a small insulating barrier. So if you're looking into that, this is a component that we need to place into these circuits to make sure that they're nonlinear, actually. And so the tunneling in that is a key component, actually. So it's really tunneling between two superconductors through a very thin insulating barrier. So yeah, I hope I didn't leave too much of your question behind. But it's very nice to see that it's pretty active. I would like to take 5 minutes. So now it's 7:21. Maybe at 25 I'll be back, and we can continue and make some quantum circuits after this small break. So thank you all. So I see that there's a question by Nicola in the chat asking if it would be accurate to think about superposition as the probability of the electron being on one or the other level. What I mean is that it's not on both levels at the same time, but rather on only one of them, but we don't know which one before we measure it. Actually, it would not be accurate, unfortunately, but like what I would like to say maybe at this point is now we're going to play with a tool that is called the Quantum Composer. And this one is a tool that will allow you to, you will not interact with necessarily a real quantum system, but it's going to mimic a real quantum system. And you'll be able to maybe develop some intuition around this. So maybe to answer your question, if the quantum mechanics were like that, like the electron is either in one of these two states, but we just don't know it. Some of the phenomenon that we're going to look at would not occur like we're going to see. Actually, there is some interference pattern actually that you can make appear, and they can only appear if you are really in a superposition of these two states at the same time. Especially when we're going to use a gate a bit later on called the Hadamard gate. I'll try to convince you that this is the case. I'm also like, it would be nice to be able to interact with like a real quantum system in front of us, like like an experiment. Unfortunately, it's not super easy. Like the circuit composer is going to, in a way, allow you to interact with the quantum world or something that's going to behave like the quantum world. So I hope you'll be able to build a bit more intuition and accept these weird ideas. So asking, would Star Trek transporter be a fair analogy to how the electron moves from one level to the other? Oh, I'm not a very Star Trek fan. I don't really know about this, but yeah, I know that these people like teleport around. You maybe could see it this way, but I'll try to maybe what the experiment we're going to do together is going to help you a bit more understand these things. But like there are some subtlety that can be only captured if you're actually doing math with this. So, but we're going to do a little bit of math in this second part. So the first thing I want to present to you is, so I guess that you're all seeing my screen. Is to show you what the circuit composer is, okay? And to do that, actually, you can go on the IBM Quantum website at this page. Maybe some of you already created an account. It's not necessary to do what we're going to do right now. There might be some of the feature you won't be available to get if you don't have an account, but you can still go on this website. And here in the left corner, you can access a couple of things. And I would like you to go on the Quantum Composer. So you can create a new file as you like that. And then you can click on this small folder to make it a bit smaller. Also on that side, maybe you have a bit of code. We're not going to work with this. So if you want to have more space, you can here close this window. I encourage you to just reshape a bit your environment so you can see a bit what's going on that in that part. All right, maybe I can. Yeah, I'm a bit limited in space, but it should be all right. All right, thank you, Michael, for sharing the link in the chat. Okay, so the Quantum Composer is this. So this looks like a bit like a partition of music. So here actually are the 3 qubits. Right now I have 3 qubits in my quantum circuit. And here what's called the classical register. So we have the quantum register on the top and we have the classical register at the bottom. So the qubit here, we're going to do some manipulation with those. We're going to manipulate the quantum information. And at some point, we're going to measure these. And when we're going to measure the qubits, we're going to find either 0 and 1. And we're going to place this value in the classical register, just here. Okay. So the gate that you can place on it, so you have a bunch of gates here. We're not going to cover all of these. We're going to cover just a couple of these. But if you want to take a gate here, you can take it, you can slide it, and you can just leave it on one of the qubits, and you can move it around just like that, okay? And you see something happening in the calculation. I'm going to look at that just a bit later. If you want to do smaller circuit with less qubit, you can always remove one of these lines. We can do, like, for example, only 1 qubit experiment. We could do 2. I think we can go up to 6. At some point, it's going to tell me that it's too much. So for 7 qubit, it's telling me that it's too much. And the reason for that is, well, 7 qubit is something that you could simulate on a classical computer. But if we could simulate like a arbitrary large of qubits on the classical computer, we wouldn't need a quantum computer. So actually, it's very difficult to simulate large number of qubit on the classical computer. So here I'm going to stay with only 1 qubit just for the beginning. So there's a couple of things here that I'm going to look at as we go. But maybe the first thing I would like to, so this is a quantum composer. And we're going to come back to it very soon. What I want to show you first is, so I'm going to go back and forth between the presentation and this website. Okay. So before we go too much in this quantum composer, I want to introduce you with a couple of tools that are going to help us to understand what's going on in the quantum world. So the first thing is the direct notation. So you remember that if you prepare a qubit into a superposition of 2 states, and then you measure it, you can either find it in the state 0 or in the state 1. Okay. So the direct notation is a way to present all these things. For example, here, I'm going to say that the probability to measure 0 is this constant alpha squared. And I'm going to say that the probability of measuring it 1 is this constant beta squared. There are some absolute values that are there. If you're familiar with complex numbers, it's just mean that alpha and beta can be complex numbers. If you're not familiar with complex number, just see alpha and beta that can be numbers that can be either positive or negative. What is very important apart from that is that you know that probability, when you have like different probabilities, you're going to find one of these results, and the sum of the probability should always be 100%. So here the probability, we're saying that it's alpha squared and beta squared, means that alpha squared plus beta squared should always be equal to 1. Okay, the sum of these two numbers should always be equal to 1. So this is how we define these alpha and beta. And the direct notation is telling us actually that the state of the qubit can be written like this. Okay, it can be written as what we call a linear combination of the state 0 with an amplitude alpha and a combination with the state 1 with the amplitude beta. You can see these actually if you've done some linear algebra, if you've seen vectors. So these states here, 0 and 1, are unitary vectors. They are basis vectors, or we call, in physics, we call them basis states. And these one are just coefficients. Okay, so this is really, this is what we call the direct notation. So here, what I'm saying right now, I could, like in words, I could say, I am in the state 0 at a certain level alpha, and I'm in the state 1 at a certain level beta. So maybe I can give you some examples. For example, I could place my qubit completely in the state 0. If I'm completely in the state 0, it means that alpha is equal to 1 and beta is equal to 0. This here would represent a qubit that is completely in the state 0. Here, I could prepare a superposition of 0 and 1. So if you take this square plus this square is going to give me 1/2 plus 1/2 is giving me 1. So this is a valid quantum state. And here I would have like 50% to measure my qubit in the state 0 and 50% to measure it in the state 1. Here is another valid state. Okay, these numbers can be negative. These states are different. This one and this one are different. But when I'm going to measure them, I'm going to have exactly the same probability to measure 0, either if I'm in this state or in this state. It's always 50% for these two. But they are different. Then they're different because when I'm going to make them interact with other qubits, these two states are going to give me some other results. It's going to do something different. They're going to act differently. Okay. So this is the direct notation for a qubit. Yes, sorry. Okay. So we're going to look at a first gate, how we transform the state of the qubit. So the first gate we're going to look at is the X gate. If you're done a bit of classical computing, it's called also the NOT gate. So the NOT gate is just, it's changing the state of the qubit from one state to the other. So if I'm the state 0 and I apply the X gate, I get 1. And if I apply it again, I'm getting back in the 0 state. Okay. So I'm going to go and try this in the quantum composer. So if I'm looking here, I'm looking for X gate. I'm not finding it. Actually, it's this one. Okay, it's the second one, the NOT gate. It's a gate that is used very often. It has a specific label for it, so this is kind of a plus in a circle. This is the NOT gate. So to remove this gate that I've put here before, I can click on it and use backspace on my keyboard. And now I'm going to apply a NOT gate. So you see that when I'm doing these things, these spectrum are changing. Maybe some of you maybe have the Q-sphere in visualization. I encourage you to have like the probabilities and the state vector. The Q-sphere is nice to look at, but is a bit more difficult to interpret. So I encourage you to have probability and state vector. So you see here now, when these two histograms, they're showing two things. Here, I have the probability to measure my system in like the probability of measurement. So here, as I showed you, I have this NOT gate. Oh, something that I forget to say, sorry. All the qubits at the beginning of the circuit are initialized in the 0 state, okay? So when this was not there, I was in the 0 state. And the probability to measure my system in 0 was 100%. This is the state vector. The state vector, actually, this corresponds to the alpha constant I was telling you about. And here would corresponds to the beta constant. Okay, so this alpha and beta. So here I'm in the states where alpha is equal to 1, beta is equals to 0, and I have a 100% of chance to measure my qubit in the state 0. If I apply an X gate, then I'm changing the state of the qubit. I'm putting it in the state 1. And I have 100% to measure it this way, and beta now is equal to 1, and alpha is equals to 0. And if I apply another gate like that, then I'm coming back to where I was. Okay, so this is the X gate. It's going to be very useful to change the state of the qubit. Next gate. Oh, sorry. Yeah, there is some direct notation here down at the bottom. The next gate we're going to look at is the Hadamard gate. So the Hadamard gate is used to prepare superposition. So when I apply a Hadamard gate on a qubit that is in a state 0, what I get is a superposition of 50% in the 0 and 50% in the 1. So actually it's 1 over square root of 2, as I showed you in the previous slide. The thing here is that if I reapply Hadamard, I'm getting back to where I was before. So in this sense, like X is proper inverse. So if you apply X, you undo what X has done. Here it's the same thing. When I apply Hadamard and Hadamard again, I'm getting back on my feet or where I was before. Okay, so maybe we can go and try this in the quantum composer. So I'm going to remove these two. So I encourage you to do exactly the same thing on the same time. So if I apply the Hadamard here, what I see is that here my amplitude are around 0.7. This corresponds to 1 over square root of 2. And I have a probability of measuring my qubit in either 0 or 1 that are roughly, actually they are 50% each. If I apply another Hadamard gate, then I come back. Yeah, sometimes the website does this. I hope it, yeah, all right. So maybe it gets stuck sometime, but for you also, just be patient. So if I apply 2 Hadamard, then I'm getting back to where I was. So maybe here we go back to the Nicolas question before, that if I'm in a superposition of state, maybe I'm just in one of these two and I just don't know it. The thing, if it was the case, each time I was applying a Hadamard, I would, like, if I prepare the quantum state and then maybe I'm in the 1 or I'm in the 0, and then I apply another Hadamard again, I wouldn't go back on my feet. I would still don't know where I am. Am I in 0 or am I in 1? Maybe just to convince you a bit more about this, is that if I apply a Hadamard on the 1 state, what I get is something a bit different. When I apply Hadamard on the 1 state, I still have these 50-50 probabilities, but here you see I have some color in the histogram. This color here, the red color, means that actually this component here has a negative sign in front of it. Okay, if you scroll down a bit, you're going to see actually that the color corresponds to a phase. If you're familiar with a complex number, you'll see that this phase here means a sign -1, and there is other phase possible. If you're not familiar with complex number, if you see some red like that, it just means that there is a negative sign in front of it. So what I mean by here is that if the uncertainty that we have, that we don't know in which state it is, and like if it was not like real superposition, that it was just our ignorance, then when I apply 2 Hadamard like that, if I do apply Hadamard and then maybe I'm in a superposition of 0 and 1, if I select, for example, 1, then it would give me something much different. But here I apply Hadamard 2 times and I'll always come back to where I was before. If I make a C naught before here, so here I'm preparing my state in the state 1, applying this Hadamard to make a superposition with like a negative sign between the 2 components, applying it back, and then I'm coming back to this 1 state. Okay, so here I get a bit away in front of myself because so these are the direct notation for these 3 states, and actually if you apply the Hadamard like that on the state 1, actually you get a superposition, but you get a minus sign between the 2. Okay. All right. So now the Z gate. So the Z gate, if you look at it and you apply it on the state 0, it does nothing. Okay. So it doesn't seem like a very interesting state, a very interesting gate. Actually, if you apply it on the state 1, what you get is the state 1, but with a minus sign. So the Z gate is a way to change the sign of the components, okay, if it's in the state 1. And if you apply it again, then you change the sign again, and you get back in the state 1 with a positive value. So we can go and test this. So if my state is in the cube, in my qubit is in state 0, and apply a Z gate, it does nothing. It stays in the state 0. But if I prepare my qubit in the state 1 first, and then I apply this Z gate, I see that my component has changed sign. Okay, so these are very basic operations. So we've seen the X gate, the Hadamard gate, and the Z gate. These are very basic operations, but we're going to build with these small pieces something that is more complicated at some point. Okay, so maybe what I would like you to do right now, I've already shown you maybe how to prepare this quantum state. I would like to try to maybe you can try to reproduce this in the quantum composer, and then try to produce this specific state. And I'm going to give you like just 1 minute. Try it, and if you find what kind of gates you need to apply to get this specific state where you have 1 over square root of 2 bar both, but you have a minus sign for the state 0 and a plus sign for the state 1. And you can maybe write this down in the chat and see if you have some interesting solution to this. You should be able to obtain this using only the gates that we've used up until now. And there are many different solutions. So for example, for A, we can use Hadamard and Z, so that's true. So we can apply first a Hadamard. So we prepare a superposition of these two states. And then when we apply Z, we can change the sign of this one. But you remember actually that you can do exactly the same thing by applying an X before and then Hadamard. So these are two different ways to obtain this result. For B, we have, I'm going to see a couple of answers, but I see that Michael is saying if you apply an X gate, a Hadamard, and then you apply another X gate, you should get this B result. So this with the red on the left and the blue on the right. And actually that's right, because what's the difference between these two? If you just exchange these two colors, you would get the right result. So exchanging these, all you need to do actually is to exchange is the X gate. So this is another way to get to it. So I'm seeing a lot of different answers. I encourage you to try it, but what you can see actually is that there are many different possibilities to get to these results. Okay, and actually another way to do this would be something like that. So this I think would be another possibility. And the reason why there is many different possibilities, if you're familiar with linear algebra again, is these gates actually are matrices. And matrices, in general, they don't commute. So if you try to change the order of some matrices, you're going to get some different result. But also what it means is that you can take different matrices and combine them in different ways to get the same result in the end. So that's why actually because they don't commute, if you change the order in which you're applying these gates, you get different result, but also you can use different combination to get the same result. So I'm very happy that you've tried the different solutions. So that's pretty nice. All right. So after that, there's the 2-qubit gates. So the 2-qubit gate is very at the core of doing what we call entanglement. Okay. So a 2-qubit gate, if you've done a bit of classical computing again, it's a conditional gate. But before we go into the 2-qubit gate, I need to go back to the direct notation and tell you a bit how we can describe a 2-qubit system. Okay. So I've shown you this a bit earlier. If I prepare my system in a superposition of 2 states, and here the superposition, it's run a certain way, but it could be like not 50%, 50%. It could be like unbalanced superposition. So there's 4 different possibilities of measurement that I can get. Oh, sorry, my computer is doing something wrong. Okay, all right. So there's 4 different possibilities, and I'm going to attach a probability to these 4 different possibilities. And a bit like we've done before, I'm going to call them alpha square, beta square, gamma square, and delta square. Okay. So these are my different probabilities, and you know that probabilities need to sum up to 1. So these value here are constrained by this relation. And the most general state that I can build out of 2-qubit is something like this. So here it's a superposition not of 2 states, but it's a superposition of 4 states. So I have 4 basic quantum state or basis state. So I have the state 0, 0, 0, 1, 1, 0, and 1, 1. And I can be in any superposition of these 4 ones. Okay. So for example, I could be an equal superposition of all the different states. This is a possibility. But I could also be in a superposition of these 2 first ones, but like no possibility of measuring these 2 ones. Okay, so these are like 2 valid examples. So this is how you build up like a 2-qubit representation, a 2-qubit state representation. And maybe I can just go a bit further by saying that you can think about this and you can ask yourself how many components like that, like so alpha, beta, gamma, and delta would be, I can call them components. How many components would you need to build if you have 3 qubits? The answer is 8. And if you have 4 qubits, it's 16, and so on. So the number of components that you need to represent the state of a system of n qubit is 2 to the power n. And again, like we were talking about quantum parallelism a bit earlier, if you have like 30 qubits, it means that if you want to try to represent the state of a system of 30 qubits, you would need to have 2 to the power 30 different components. And this is a very large number. Okay. So what the CNOT gate does? So the CNOT gate is a conditional operation that involves 2 qubits. It's a 2-qubit gate. And there is a control qubit, and there's a target qubit. And the idea is very basic, is that you're going to apply a NOT gate on the target qubit only if the control is in the state 1. If it's in the state 0, you don't do anything. But if it's in the state 1, you change the state of the other qubit. This is basically what a CNOT is doing. If it was classical computing, this is something that would be useful to do additions and stuff like that. But now, because we have superposition, we will be able to apply CNOT and not apply it. So if the qubit, the control qubit, is in the superposition of 0 and 1, you're going to apply the CNOT, and you're not going to apply it, both at the same time. I know this is weird, but this is what's going to happen. So here, just a picture just to represent it graphically. So if I have 2 qubits like that, and I apply a CNOT, so the CNOT is drawn like this. This is the control qubit. This is the target qubit. So this here you see you're applying a NOT, but it's controlled by this qubit. And here in this case, the control qubit is in state 0, so nothing's happened. On the other hand, if my control qubit is in the state 1, and apply a CNOT, then I'm going to change the state of the target qubit from 0 to 1. The other way around would be also right. If here I was in the state 1, I would need to flip it, and it would finish in the state 0. Okay. So we can go in the quantum circuit composer and maybe to experiment with this a bit. So I'm going to remove this one. And then I'm going to apply a CNOT, so on the 2 qubits. So now you see, so the labels here in the probability and the state vector have changed. So now I'm getting the probability to measure either one of the 4 different possibilities. And here are the component alpha, beta, delta, and gamma, how I've defined them earlier. These are components be in front of these 4 different basis states. So here, if I do that, nothing's happened. But if I have my control qubit in the state 1, then I see that I'm changing the state of this qubit. But now the CNOT is also going to change the state of the other qubit. So now both qubits are in state 1. If both qubits were in the state 1 before, then I would finish in something like that. And maybe this is the right time to explain to you that how you can read this. So just to make sure it makes sense, the qubit on the right is the one that is on the top. It might not be super intuitive, but this is the way that you can write numbers from 0 to 3 in binary form. So this corresponds to 0, 1, 2, and 3. Okay, if you're familiar with the binary form of integers. All right. So now I didn't try to apply the Hadamard gate at the same time because I want to talk to you about entanglement before. So how can you create entanglement with a CNOT? So the entanglement, as you remember, is the fact that we create a superposition of either both qubits are in the 0 state or both are in the 1 state. So this is entanglement. So how can I start from a system where both qubits are in state 0, and I prepare this specific entanglement state? So I'm going to show you the recipe. You first start with the both qubit in the state 0, and you apply a Hadamard on the qubit, on the qubit that is on the top, the qubit that is on the right here, like that. So I'm going to express this more explicitly, like that. The Hadamard is going to be applied on this one. So here I'm using the direct notation. This is something that happens really often. This is the two qubit state, but I can factorize it into one qubit state. But I just need to make sure that I keep the ordering of this, and I follow it, and I make sure I don't mix things up. So now I can apply this Hadamard gate on this qubit 0. By that, I prepare a quantum superposition of these two states. And then I can combine these two one together, give me the state 0, 0. Then I can combine the state of the qubit 1 with the state of the qubit 0, and doing like that. So now, applying the Hadamard only on this qubit, I have prepared this quantum superposition. I mean the superposition of both in the state 0 or both in the state 1 and 0. So actually what you're seeing is that only the qubit on the right or the qubit on the top here is in the quantum superposition. But now the magic happens. I apply the C0 on this. So when I am going to apply the C0, I'm applying this is the control qubit, and this is the target qubit. So applying on this changed nothing on this one. But then when I apply it on the second part, now I see that the control qubit is in the state 1, so it has to change the target qubit, and then it changed this one. And this is how you prepare this quantum superposition. So by doing that, applying a Hadamard on the first qubit, and then applying a control knot from the first one to the second qubit, I can prepare this quantum superposition. So I'm going to go back here just to show you that it works. So applying a Hadamard and then a control knot. What I'm preparing here is a quantum superposition of 0 and 1. So the state vector is exactly what I was telling you, 1 over square root of 2 on that side, 1 over square root of 2 on that side. There is no possibility of measuring one qubit in the state 0 and the other one in state 1. Either the two qubits need to be exactly in the same state. And when I'm going to do the measurement, I'm going to either find both in the state 0 or both in the state 1. So maybe right now, maybe some kind of exercise, maybe are you able to prepare this kind of quantum superposition? So, excuse me. So here you're trying to build a superposition not of both qubits in the same state, but qubits that are in different states. So this is the challenge here. And here is both qubits are in different state, but also there is a different phase between these two possibilities. So again, I'm going to leave you a couple of a small moment to think about this and try things in the quantum composer. It's a bit of a harder problem. So we have an answer here. Okay, all right. So Stefan is telling me that he applies a Hadamard and a C0 and then a knot. So of course, doing that, applying a knot maybe on the first qubit is going to change the state of this qubit here for 1 to 0, but here from 0 to 1. Just exactly, this is what we're expecting. So that's nice. But the thing is that I could have applied it here too, and it would also work. The only difference is that in one case, it's this part that is going here, and this part is going there. But if I apply the C0 on the bottom one, then this weight here comes here, and this weight goes there. Maybe I can try. Maybe I can try for B. I'm being said I can apply here this one. So here, by doing that, this is the more advanced, but this is true. This is a bit more complicated to follow, but this is working right, because we know that applying a Hadamard on a knot is preparing a superposition of 0 and 1, but with a minus sign. So now applying this C knot is going to still prepare this superposition, but we have a minus sign in front of this one. And then how we need to do is, again, maybe just flip this. I don't know if it's exactly the same or it's not exactly the same. So as I was saying, if I put it on this one, then the weight that I was in 1, 1 goes on the 0, 1, and the weight that is on 0, 0 goes on 1, 0. So maybe for some of you, maybe a bit fast. I have a couple of answers very interesting in the chat, so that's nice. But you know, you can take the time later on to experiment with that and try to understand and make sure that it makes sense. This is something that is pretty new. Like, people were not able to experiment with quantum mechanics before. It was not something that was easy to do, but now with this kind of tool, it's kind of interesting, and you can play with this. So we've played a bit with this, and actually, and now we've seen that we can prepare entanglement. And here, what I want to show you is that actually there is. I've already told you that with 2 qubit, with 2 qubit, there is 4 basis state: 0, 0, 0, 1, 1, 0, and 1, 1. And actually, you can start with all these 4 different basis states. This could be like your starting point. And then you can apply this entanglement circuit, the Hadamard and the C knot, and then you would get something. And actually, you're going to get 4 different things. And these 4 different things are the Bell states. So the first Bell state, we already seen it. It's a superposition of 0, 0, and 1, 1. And both coefficients are positive. The second one is kind of the same thing, but one of the coefficients is negative. The third one is you have this odd states where one is in the 0 and the other one is in 1 state, but with both positive coefficient. And then you can have the third one where you have this odd configuration with a negative component. So maybe if I come here and I play a bit with this, so this is the way you can prepare the first quantum state and the first Bell state. Sorry, been speaking for 2 hours. I'm going to lose my words. So, but if I apply this circuit on the state 1, 0, I get another Bell state. And if I apply it on this one, so here I'm applying the Hadamard and the knot at the same time, but this doesn't care, it's not a problem. I'm getting the third Bell state, and in the end I can get the fourth Bell state. So this is, so for people who have done some linear algebra, this is just a basis change actually. I have a basis to represent the state of 2 qubits, and here I'm changing this basis state from the basis state that I already know to something that is a bit more bizarre, and this is the Bell basis state. Okay. So why am I telling you this? It's going to be very useful for the quantum teleportation. So now I want to. So these are the 4 ways you can build these 4 Bell state. And now what I want to show you is that there is something called the Bell measurement. Okay. If I come back here, I'll come back to this one, but if I come back here, whatever I prepare before applying this, I know that I can undo it by applying a C knot and then a Hadamard. Okay. The inverse of a C knot is a C knot. If I apply a C knot twice, I get back where I was before. So I could just cancel these 2. And then I apply a Hadamard after a Hadamard, and I know that these 2 cancels out, and I'm getting exactly the same result at the end. So why am I doing that here? Actually, is to tell you that there is something called the Bell measurement. So the Bell measurement actually is something where, okay, and yeah, I just realized that I didn't show you the measurement yet. Okay, yeah, I'll need to take time to do that. So these are the measurement on the qubits. I should have done that like way earlier, but we'll come back to that. But the idea here is that if I have a circuit here that is hidden by this red box that prepares a specific Bell state, then I can undo it and try to measure it. And I'm going to see if I find 0, 0, that means that at this point, I was in this specific Bell state. Okay. If I measure 1 and 0, 0 and 1, so this means 1 on the top and 0 here. If I measure that, it means that I was at that point here. I was in this specific Bell state. So this is called the Bell measurement. Okay, I need to apologize. I didn't show you the measurement before. So I'm going to take just a bit of a moment to explain to you what the measurement is. So I'm going to go back to one qubit. And what I'm going to do is this is the measurement. This means I want to know what's the state of the qubit. So here it doesn't change much, okay? If I change the state of the qubit and I measure it, it doesn't change much. It gives me mostly what I had before. The thing is that if I prepare my qubit in a superposition, and then I need to measure it, I'm trying to measure it, I'm going to pick one of the different possibilities. Okay, when I measure it, I'm changing the state of the qubit, and I'm going to find either 0 or 1. But now there's no superposition. I've changed it. This is a simulation, and actually I can change the state, the result of the simulation using different random numbers. So if you're familiar with like pseudo-random numbers, you know that you can change the seed to these random numbers. So this is kind of saying, oh, try different random possibility. So if I change this value, you're going to see that the state of the system is going to change from one another from time to time. Now it's not changing very often, but if you test like maybe the first 100 seeds, you would get 0 roughly 50% of the time, and you would get 1 roughly 50% of the time. Okay. And then being said, maybe I can also take the time to show you that we can actually run this on a real quantum computer. So this is only simulations, but I can run this on a real quantum computer if I'd like to. So the people that are, if you subscribe to the website and you're not running this as anonymous users, actually, if you build a circuit like that and you have some measurements, you can run this on a real quantum computer. If you put no measurements, you will get just 0. If you put no measurements, your classical register is going to stay in the state 0, and you will not see anything happen. I'm going to show you quickly how to do this. So if you want to run this measurement, you can come here and set up and run. And you can select a backend, so a processor. Here I have access to this 25 qubits processor. Most of you don't, because this is part of the IBM-Q, the S-Plus IBM-Q privilege. But here I could take the Armonk, for example. Armonk has only 1 qubit. That's all right. I only need 1. So if you have access to this one, you could run this like this. Here, your provider might be different. You might be having open main here if you've subscribed. And what I like to do actually is run this only 1 time. So here is the number of time I'm going to run the circuit. We're going to go much into this, but usually a quantum circuit, you need to run it a really high number of times to deduce some statistics on the result, and you can get some interesting information. So first, I'm going to run this only 1 time. If there are some people in the audience that have this kind of account and they want to try it and run this circuit with 1 Hadamard measurement and run it only 1 time, that would be nice, because we're going to see that we get different results. So if I run it like this, I'm going to run it at least twice. Is it still selected on Armonk? Yeah, I'm going to run it. So if you do that, you're going to see here on the left that you're going to tell me that the jobs are pending. Actually, my first job is running right now. So these processor, they're in high demand sometimes. So you might be waiting for your turn to do a calculation. It happens. And when your job has been selected, you're going to get some result. So you see here, I've built this circuit, prepare a superposition of quantum superposition of 0 and 1. I measured it, and I find my result in the state 1. Okay, I measured it only once. If I go back in my different jobs, the other one also is completed. I also get the number 1. Maybe if some of you have tried it, maybe you've got 0. So this is just a like an example of that. This is randomness. Just to conclude this, I'm going to maybe run it 100 times. It's going to send this circuit to a real quantum computer. So these are real experiments going on into a lab in your town. I'm going to wait just a bit. And you see the experiment here, what I have is I got 0 a couple of times, I got 1 a couple of times. You see that there is some imbalance in here. There is 2 reasons for that. 100 shots is a pretty small number, so I can have some statistical noise that's going to interfere with this. And the other thing also is that the R-Monk qubit is not a perfect qubit. Okay. Actually, it's not the best one. It's kind of old now. And if you remember, the state 1 is the excited state, and the state 0 is the ground state, is the lower state. And there is a certain probability, certain chance that the state is going to go down in energy. It's going to relax, and that's why we have a greater chance to find 0. So this is one kind of error that a quantum computer can do. And these errors, this is complete other topic that I will not cover right now and today, but this is something that is one of the big challenge to make the quantum computer very useful in the future. All right. So I've shown you the measurement, and I've shown you how to run these on the real quantum computer. Also in here, there are some other simulators that are more advanced, and they make it possible to simulate circuits that have more than 7 qubits if you want to. So now that we have seen the entanglement, like with the CNOT, the Bell states and the Bell measurement, we're going to be able to tackle the teleportation circuit. Okay. Maybe I can take a moment to drink a sip of water and see if there are any questions in the chat. Okay, I guess you're either all very tired or very eager to see what teleportation is. So let's go going. So quantum teleportation, just so you know, it's something that has been invented partly in Montreal, at Université de Montréal. There's these names here on this paper from '93. Gilles Brassard, Claude Repault, and Richard Josa. They were all based in Montreal when they invented quantum teleportation. So this is like a couple of years ago, in '93. And then was kind of a crazy idea. People were not doing quantum computing at that time. People were thinking about this, but there were no experimental realization of these things. And just a couple of years ago, like 4 years ago, and since now, actually this is one of the best experiment. One of the that strikes the imaginary most is in 2017. So this is a China research group that was able to do a quantum teleportation from a lab in China to a satellite that was 1,400 kilometers in altitude. So they were able to use light and it's mostly photonic experiment, but they were able to show that they were able to use a Bell pair to teleport some information into a satellite at a very large distance. But there were other realization of that at smaller scale in labs. This is something actually now that is done like mostly every day in some labs. So, but this is maybe the most striking experiment on that thing. So before we go into teleportation, there's this cloning theorem. There is a mathematical proof that I will not show you today. You can find it pretty easily on Wikipedia, for example. But the idea is that unlike classical information, you cannot copy information in the quantum world. Actually, you cannot copy arbitrary unknown information. So the idea here is that if you have a qubit that is in a superposition that you don't really know, you know it's in a superposition, but you don't know the coefficient alpha and beta. And you would like to copy this information in another qubit. So doing something like that. So to have two copies of this same information, but this is like an arbitrary state. So you would use like a 2-qubit gate that would call quantum copy paste, but this is not allowed. Maybe like for people that are more familiar with linear algebra, here it's because all the quantum gates need to be unitary. And so if it's unitary, you would need to be able to inverse this. And because here, if you have these two states, how can you inverse this? You don't know which one was the original qubit, which one is the one you copied information to. So this is kind of a hand-waving argument, but you can strictly prove that you cannot copy arbitrary unknown quantum state. You can copy like state that you know that are like, if you prepare a qubit in the state 0, you can make many copies of this, but you know that the qubit is in a state 0. Here, what we call arbitrarily unknown quantum state is a quantum superposition that is very, very arbitrary. So this is kind of so I have just a comment in the chat that saying that being a bit impressed that linear algebra can help model quantum computing mathematically. Actually, linear algebra is the mathematical tool to represent quantum computing at large. When I was showing you the quantum state, the different components, you need to put that into a vector. And all the gates, either the 1-qubit gates, the 2-qubit gates, and you can imagine 3-qubit gates, these are matrices. These are matrices that you can apply. So yeah, we like to say that like people asking the fundamental question of what's linear algebra good at? When you learn that sometime at the beginning, you don't know what is it for? Quantum computing is a very good example of where it's very useful. All right. So quantum teleportation, I'm going to try to explain to you a bit what is the protocol. This is also a bit it's difficult to represent like quantum information on a piece of paper or a computer screen, but try to follow me. So the idea is that we have these two quantum people, Alice and Bob. Maybe you've heard their name before. So Alice and Bob are on Earth at the beginning. They both have a qubit. And what they're going to do first is they're going to entangle their qubit. So they're going to do this Hadamard CNOT on their qubit. And so these two qubits now are in entangles superposition. So they're like correlated together. If I measure Alice, it's going to change the state of Bob qubit. And then Bob live in the space, lives on the moon, I don't know where, but it goes away. He goes away. Then Alice has another qubit that is in the arbitrary quantum state. I don't know what the state of this qubit is. And the goal of the teleportation is going to take this information and send it on Bob's qubit. Okay. So to do that, Alice needs to make something, needs to mix our two qubit that she has, the qubit that is part of the Bell's pair, and the mystery qubit. So she does something like that, and by doing that, so she mixes them by doing actually a Bell measurement. But by doing that, she entangles these two qubits. But because the two first qubits are also entangled, all of this system is now entangled together. So now it's a 3-qubit system that is in a quantum superposition of actually many different states, up to 8 states actually. Then, so what actually Alice is doing here is she's doing a quantum Bell measurement on her 2-qubit. So by doing the measurement, she gets 2 classical bits out of this measurement that are either 0 and 1. And she takes these bits and she sends them, so maybe she gets a 0 and 1 like that, and she sends this information to Bob in space. So also by doing this measurement, because all these 3 qubits were entangled in a system before, this is also going to influence what Bob's qubit is. And actually, Bob's qubit at this point is very close to the state of the mystery qubit at the beginning, but might be two qubit operation away from this. And the operation you'll need to apply are going to be dictated by the two classical bits that Alice needs to send to Bob. Okay. Bob received these two bits, is going to transform his qubits according to these results. And at the end, Bob's qubit is exactly in the state that the mystery qubit was at the beginning. Okay. So this was the protocol. Now we're going to try to build the circuit. We're not going to teleport arbitrary state because we want to see if it's going to work. So we're going to use a specific qubit state to teleport. And this one is prepared with a specific gate. It's called a RY. So it's a rotation around the y-axis. We're going to use an angle of -π/3. And the idea of this actually is going to prepare this specific state. So we have the component square root of 3/2 and -1/2. And if you take the square of these value, what you find is 3/4 and 1/4. But the amplitude have different values, different signs actually, but one has 3/4 of time a chance to be measured and the other one have 1/4 of chance to be measured. Okay, so we're using this because it's kind of general and kind of easy to follow. So this is the quantum teleportation circuit. I'm going to go and build this in the circuit composer. So I'm just going to just show you the different parts. So the Q0 here is going to be the mystery qubit to be teleported. And the two other ones are the two qubits that are part of the Bell pair. Okay. I'm going to label them M, A, and B. Then we prepare the specific state we want to teleport. And also we prepare the Bell state between the qubits of Alice and Bob. Then Alice on her side needs to do this Bell measurement. So she applied these two gates, but in the reverse order on the two first qubit. And then she measured the qubit. The value of the measurement are sent to the classical register and sent to Bob. And then Bob needs to apply a specific gate dependent on the value of here. So what exactly the gate that he needs to apply is a NOT gate if this qubit is in the state 1. This bit, actually, this classical bit is in the state 1. And apply a Z1 if the other qubit is in the state 1. So let's go and prepare this quantum circuit on the circuit composer. So I'm going to erase that. I'm going to prepare 3 qubits. So you have a question, how can you move the barriers so it's readable? So maybe you're trying to apply barriers. I'm going to show you how to apply barriers just in a moment. So the first thing we are going to apply is this RY gate. And by default, we have this π/2 value as an angle. So if you double click on it, you can come here and change this value. I'm going to use -π/3. And you can click here to go back to your circuit. Then the barrier are these things. If you go and you look at this, there are some barriers. The idea of these barriers are twofold. Either make a circuit a bit more readable, so I can draw it here. But you see, I'm now applying only on 1 qubit. If you double click on it again, you can select to apply it on the 3 qubits. So this is the first use of the barrier. The other use of the barrier, like the real use of it actually, is to prevent some recombination of gates. So you already tell you that some gates cancel each other. If some gate is in its proper inverse, they're going to cancel each other at some point. And actually, when you send a quantum circuit to a real quantum computer, this cancellation is going to be carried out to make the circuit as simple as possible. If you want to prevent this, you can use barrier. So if you have 2 gates on both sides of a barrier, they will never be recombined together. You might have some good reasons to do that. All right, so we have the first qubit that is prepared in our superposition. And then we're going to prepare the Bell pair. We have a question. So we're sending information to Bob under the former classical bits. Aren't we just traveling through space at the speed of light rather than teleporting? Actually, this is very important remark. So actually, you cannot go faster than the speed of light. This is something that Einstein told us, and we verified it also. But so the idea here is that, like the teleportation, as I was saying at the beginning about the no cloning theorem, it's really because we cannot clone information that teleporting is so important. So I can move some arbitrary quantum information from one qubit to the other using quantum teleportation. This is something that could be done inside a quantum chip, actually inside the same quantum computer, and would be still useful. But you're right that you cannot move faster than light, because you need to send these two classical bits classically to Bob for the information to be carried away. You can show also mathematically that if Bob does nothing on his qubit, there is no information stored in Bob's qubit as long as he does not perform the two operation on it. So. And maybe the other comment, but aren't entangled qubits react faster than the speed of light? So kind of, yeah, but there is no information traveling from one qubit to the other, even if they weren't entangled together. So this is more advanced topics. There is some mathematical proof for that, but like the objection that you have right now is exactly the objection that Einstein had. But like learning a bit more about it, people think about it. You can like clearly prove that you cannot send informations faster than the speed of light using like entangled pair like that. Maybe I can ask the other question right now very rapidly. So is asking if I just use this graphical interface to code. Now, actually, this is very pedagogical tool that is very useful to show quantum programming and quantum circuit. But actually, we use Python and Qiskit to do this kind of work when we want to build larger circuit, especially like, for example, quantum Fourier transform and stuff like that. You cannot do this by hand. It's going to be too long. I can comment a bit more on that at the end of the session. Okay. So we have our qubit, we have our Bell pair. Now we're going to apply another barrier. I like to put barriers mostly everywhere. Coming back here, and then we're going to apply, we're going to do the Bell measurement. So we do this here, and you see the things happening down here. We're going to go back to this as soon as we're finished building the circuit. And then we're going to apply a barrier here. And then we're going to do a measurement. Actually here, I'm going to do something a bit fancy. I'm going to use not only one classical register, I'm going to build two classical registers. So to do that, I can go into edit, and I can come here and manage register. And you're going to understand why I'm going to do this. Here I can manage the register. So you see here I have this quantum register with 3 qubits. That's all. That's all right for me. And here we have the classical register, and we have this checkbox to synchronize the number of qubits and classical bits. I'm going to uncheck that, and I'm going to build two classical register with only 1 bit in them. So this one I'm going to decrease it to 1, and I'm going to add another classical register, and I'm going to have only 1 bit to it. Actually, maybe I can. Oh yeah, so that's all right for that. Now I'm going to save this. So the idea here to do that is going to be make things easier when I'm going to want to apply the gates that Bob needs to apply. So now I can measure this qubit, measure this other one, and you see that here what I want to do is do the measurement on this qubit, send the information on the first classical register, and the measurement of the second qubit, I want to send it on the second register. So I'm going to edit this one, and I'm going to say to send it to the second register to have something like that. Okay. So now the measurement is done. What remains to be done is to change the state of the qubit with the proper rotations. So if I remember correctly, I have to apply a NOT controlled by the second register and a Z controlled by the first register. So I'm going to move these here, this one here, and this one here. And to make them conditional to the values that are here, I'm going to apply an if operation like this. I can do this the same here. And now I need to modify this. This one, I need to make sure that this is conditional on the second register. And I'm only going to apply it when the bit is in the state 1. And this one is controlled by the right classical register, but I need to make sure that is when it's in state 1. So this is the circuit, okay? So, yeah. So, yeah, I'm just going to skip this. So the idea is, okay, so yeah, so now, now I'm going to go back. So it maybe here it's just a, just going to, okay, so this is the complete circuit, and this is the result that we get. So I've been a bit fast showing you like these gates. So what I'm going to do, I'm going to go into the inspect here, and inspect here, what it allows me to do is going to show me the state of the system at each different step in the circuit. So for example, here I apply this rotation. I see that I'm in like a weird superposition. So actually the labels are a bit off, but I'm going to move around and it should fix it. Yeah. Yeah, this is weird. I never encountered that, so I'm very sorry. I don't know why it's doing this. Maybe because I only 2 measurements, but anyway, what I want to do is to go at this point. And so maybe forget about the measurement probability, look at the state vector, okay? So at that point, what I see is that I'm in a superposition of all the 8 different possibilities, okay? And some are of a probability square root of 3/2, and some are of probability 1/2 actually. But they're spread out, so actually here the amplitude is 1/4, and this exactly, I think, is square root of 3/4. But because all of these, when I square them together, this should give me 1. So this is the histogram that we have here, and this is the same histogram. So now we're going to try to deduce what are the action that Bob needs to do on his qubit. So I put them already. I've sold the punch for it, but we're going to try to deduce it. So for example, if I'm here just before the measurement, so if Alice does our measurement, she measured the 2 qubits that are on the right side. So if she measures 0, it means that she measured the state this and this. So she's going to project the whole system into the subspace where both these qubits on the right are 0. Okay, and if she does that, all the rest is just forgotten. And what you see is that you're exactly in the right state. This is the state that I prepared in the beginning, meaning that the qubit here, the third qubit, has a 3/4 of chance to be in this state, and as in the 0 state, and has a 1/4 of chance to be in the other state, but with a minus sign. So if Bob receives, so if Alice actually measure the 2 qubits in the 0 state were projected in this specific situation, she sends these 2 values to Bob. Bob receives 2 0, and now he knows that he don't need to do any operation on his qubit. There is no operation to do, and this qubit is already in the state that wanted to be teleported in, okay? The second possibility is this one. So if Alice measures a 0 and a 1, so a 0 and a 1, a 0 and a 1, she's in this, the system is in this situation. And what you see is that you're almost in the right state. The thing is that they're flipped around. You would like to have this probability to be in the 0 and this into the 1. So you need to apply an X gate. So if Bob apply, oops, sorry. So if Bob apply an X gate, it will correct the state of his qubit to be exactly in the qubit. So from this to there, is there an X gate between the two? Okay. And now we can go on with the third possibility. If Alice measure 1 and 0, so now the system is in this configuration. Now you see that the probability or the amplitude are the right one, but the sign is not good. We need to change the sign of this one. So we need to apply a Z gate on this one. So applying a Z gate, we're going to change the sign of this particular component. And the fourth possibility, if Alice measured 1 and 1, she sends this to Bob, Bob received this. Now he knows that his qubit is like the amplitude are flipped, and you also need to flip the sign of it. So he needs to apply a NOT and a Z. So this is how you can deduce it. You can do also mathematically. It's a bit faster, but this is maybe the most intuitive way to understand what are the gate that Bob needs to apply on this qubit to make sure that the teleportation protocol is successful. So this is the circuit. And now if I come back here, the circuit that we already done, and I quit this inspector. So what you see now is that at the end of this circuit, my system is in the state of the two qubits, the top one that have been measured by Alice, are always in the same value. These are always going to be the same. They have been already measured, so there is no superposition. The superposition is only on the third qubit, the one on the left. And what you see is that we have the right proportion and we have the right relative sign between the two. And now if I change the seed, so the seed is going to pick randomly what is measured here. But if I change the seed, what you're going to see is that the state of the third qubit is always the same. The state of the two first qubits are changing. So that's why it's moving from right to left. Because the two qubits on the top, we don't control them. Alice is going to measure them. And it's going to be one of the 4 different possibilities all the time. But the third qubit is always in the right state. So we've successfully done the teleportation protocol. Okay, so maybe it was a lot of information to swallow at the same time. But if you want to try to experiment with this, you can. And also, you could also change here for example, the angle of this rotation. You could use maybe pi/8. You come back and now you see that the initial state is changing, and but the teleportation is still working, whatever the state you're trying to teleport. All right. So actually, this is mostly the end of this workshop. What I just want to add, if you want to go a bit further with this. So one of the questions asking if we are always using the graphical interface. The answer is no. Actually, maybe I can show you something. At the beginning, there was this code editor that was on the right side. So if you come in here in the view, you can see that this actually generates a code in Python that actually use the Qiskit module to build the circuit. So if you would like to experiment with that and be a bit more serious about it, and you want to learn Qiskit, then you can start with something like that. You can build your circuit here, and then it would give you the code to generate this kind of circuit. If you're logged in the IBMQ experience website, you can open this into the Quantum Lab. So this is a Jupyter notebook, and you can code directly in this web interface and interact with the quantum computer in the web interface. So this is something that is pretty nice, but you need to create an account on the IBMQ experience if you want to work with that. So if you want to learn about Qiskit, there's a lot of documentation. This Qiskit textbook, actually Sean already mentioned it. It's pretty nice because it's open. It's open source. People can contribute to it. But what is nice is that if you read it, you try to do the exercise, You will as well learn quantum mechanics, and you will learn to use Qiskit both at the same time. So it's not just covering Qiskit tools and Qiskit different methods. It's also covering some quantum mechanics subjects. So it's a pretty nice tool. And then from there, you can also go into the Qiskit documentation and having more information on what are the different tools that exist in Qiskit. Some of these tools don't have like tutorials to show you how to work with them yet. So, but maybe it's going to come at some point. If you are like a YouTube watcher, you can go on YouTube. There's this Qiskit as a YouTube channel, and there is this coding with Qiskit. Actually, now they have season 1 and season 2. Season 1 is very nice to just set up your environment on your computer, install Qiskit, playing with your first code, and learning a bit about this. The second season goes more into some specific application. If you're familiar with the different topics they're trying to cover, it helps. Sometimes they don't take always the time to introduce everything, but there is some nice application examples in this. And there are also a bunch of seminars, technical ones, introductory ones, and some other things like Qiskit, coding with Qiskit minutes or something like that to learn some very useful stuff. One of the last things I want to tell you is that Qiskit actually is built in 4 different modules, if you're interested into that, called, actually, yeah, there's a bit of a change in there, but usually it was called after the 4 elements. So Terra, Ignis, Aqua, and Air. So Terra is more about the circuit creation. So what the code that I was showing you is mostly Terra code. Ignis is for error mitigation and characterization. It's pretty nice. Aqua is now like deprecated. Aqua encapsulated all the different application in finance, chemistry, optimization, and machine learning. Was becoming too large, I guess, and IBM Q decided to divide this into sub-modules. So Aqua is now deprecated. And Air is all about simulation. So all the simulators are available in this sub-package. So actually, I've stolen this slide from one of my colleagues. So this is not my web address, but anyway. So I don't know if you have any question on that. If you want to discuss, I'll be here for a moment still, and I welcome any questions. Also in the email, most of you probably received it. I've sent you the link to the 2 questionnaires that we've built up, one for appreciation of this workshop. We'd like to have your opinions. And also there is evaluation of what you've learned. So there's 3 small questions in this form. So we'd like to encourage you to maybe fill this in the next 24 hours when the ideas are fresh. But I think it will not take you too much time. So I guess that every one of you have already these links in the email I've sent earlier. But if it's a problem, I can also copy them in the chat. So just let me know. Yeah, thank you, Michael, for sending the links. So we have another question. So other than linear algebra, Python, C++, are there any undergraduate courses you'd recommend if we're interested in quantum programming? I would say that quantum physics, quantum mechanics. So we've covered some of the basic, but like very shallowly. If you want like to work a bit more with this, to be familiar with the direct notation, and also just not to be familiar with linear algebra, but linear algebra apply to quantum mechanics and quantum computing. I think that a quantum computing course, quantum mechanics course would be useful. Ideally, what we call spin-based quantum computing. So there's, if you're familiar with or if you're not familiar, so historically quantum computing was about wave function and trying to describe the behavior of like wave particle dualities and stuff like that. And like this is kind of a generalization of a much simpler version of quantum mechanics that usually is taught later, and that's kind of a weird thing to do. But when you start with qubits, quantum mechanics is very simple. It's like qubits is a 2-component vector, 2 qubits is a 4-component vector, and then you can build on that. When you're playing with wave function, you're playing with infinity large or continuous vector and stuff like that. So it's a bit more abstract. So, but I would recommend to get a quantum computing class. Other than that, I would say that if you want to make a difference into right now in quantum computing, to be an expert in something that can be applied, or on which quantum computing can be applied, is also great. So if you're very good at chemistry, for example, and you know a lot of things about chemistry, and you want to apply quantum computing to this, you're going to have a edge on a lot of people. So bringing these two things together, either what is the other thing, could be chemistry, finance, physics, hydrodynamics, I don't know. But I think would be a huge bonus for you.